Nakamute pala ako. Good afternoon, everyone. So, hindi ko alam kung nakapagpakita na ako sa inyo ever. Ngayon ko lang na-realize, patapos na yung SEM. Baka hindi nyo pa rin ako nakikita. So, on ko yung camera ko for the start of the class. Also, if you want, you can turn on your cameras para makita-kita man lang tayo kahit sa second to the last or third to the last meeting for the semester. So, yeah, good afternoon. And bago tayo magsimula, tingnan natin yung timeline natin because we only have one full week for the semester. So that's going to be this week. And I'm thinking of sana matapos natin yung coverage by this week para hindi na tayo mag-meet on the 21st and you can devote it on the problem set. Pero let's try kung kakayanin natin isingit lahat ng mga natitirang topics until Thursday. So, but before that, I hope you got to see your third problem set. I think I already graded. Hold on. Ayan, I hope I'm back. Sorry about that. So I was saying sana ma-compress natin lahat ng contents ng course until Thursday so we don't need to meet on Tuesday next week para ma-devote nyo yung Tuesday next week para sa huling problem set. So nasoli ko na yung problem set number 3. I apologize for the bit of a delay. Dapat mas maaga ko siya nabalik pero sinulit ko yung bakasyon ko 2 weekends ago. So if you have some questions about it, just let me know. Send me an email or a chat via Teams and I'll be more than happy to explain kung bakit ganun yung nakuha yung score para doon. And then the last problem set will be given on December 16, 8 a.m. kay Canvas. So that's going to be when? That's going to be on Thursday. Tapos ang deadline niya ay December 24, right before your Noche Buenas. And then yung final project, which is 10% of your final grade, will be due on either January 7 or the schedule of the final exam, whichever comes later. So it's either January 7 o kung kailan yung finals na ibibigay sa atin ng registrar. Okay? Pero ibibigay ko na yung final exam question or guidelines sa December 21. Para masimulan nyo siyang gawin by siguro end of day December 21, some of you will be able to submit the final exam right away. Tapos it will take me a day or two to finish grading everything. Makikita nyo na yung final grade nyo sa Math 155. All right? So I hope that timeline is good. Tinatry ko siyang i-expand kasi alam ko ay marami rin kayo mga courses ngayon and most likely naghahabol din silang lahat ng mga requirements. So hopefully that timeline for Math 155 is good for you as well as mapagaan niya yung natitiran yung mga workload para sa mga susunod na araw. Okay? Now, with that out of the way, let me turn off my camera. Tapos simulan natin yung discussion for today. Okay. Oh, by the way, I made some last-minute changes dun sa lecture notes. I made some corrections, especially starting dun sa i-discuss natin ngayon na criteria for integrability. But let me use the old notes first. Tapos para ma-retrace natin kung ano yung mga ginawa natin last meeting. And then I'll shift later to the latest version of the lecture notes. Ka-upload ko lang siya siguro mga 3:53 this afternoon. Katatapos ko lang siyang i-edit. So you can download the latest version via the Canvas link. All right? So last meeting, we talked about integrability criterion and we said na may mga mas madaling paraan para ma-check kung ang isang function ay Riemann integrable or hindi. Kasi kung babalikan niyo yung definition ng Riemann integrability, dapat sa kahit anong partition inducer, yung supremum or actually kukunin natin lahat ng possible partition inducers nung closed interval AB. Titingnan natin yung mga lahat ng posibleng upper and lower sums. Tapos kukunin natin yung supremum ng lower sums. Kukunin natin yung infimum ng upper sums. And if they are equal to each other, then we say that the function, by definition, is Riemann integrable. All right? So, napaka-tedious ng proseso. So, last time we developed the integrability criterion, which says it is sufficient to issue a challenge epsilon at maghanap tayo ng partition inducer P such that the difference between the upper and the lower Riemann sum would be less than epsilon. Now, ganito naman talaga yung idea. Gusto nating mag-meet halfway yung upper at saka yung lower Riemann sum. Kasi napakita natin na yung lower Riemann sum ay laging mas maliit sa kahit na anong upper Riemann sum, kahit magkaiba yung partition inducers nila. But the integrability criterion, that is Theorem 5.1, tells us that if we can make the difference between the upper and the lower sum, okay, corresponding to a partition inducer P to be arbitrarily close to each other, so pwede natin silang mapaliit. Yung difference sa kanila ay mapaliit, mapalapit yung upper Riemann sum sa lower Riemann sum for some partition inducer, then that is sufficient to conclude that the function is integrable. So mag-i-issue tayo ng challenge na epsilon, dapat mabigyan tayo ng response na partition inducer na napakalapit na ng upper sum sa lower sum. And if we can do this for all challenges epsilon greater than 0, then we can say that the function is Riemann integrable. Okay? So ito yung pinaka-basic na integrability criterion. But thanks to Theorem 5.1, we will have some classes of functions that are known to be integrable right away. So nandito yung Theorem 5.2 na kapag meron tayong bounded function, idagdag ko lang sa pagiging bounded yung pagiging continuous all throughout the interval AB, then automatically we know that f is Riemann integrable. Okay? But again, there's a caveat here. Dapat mag-start ka sa isang bounded function. Kasi pag yung function ay unbounded, hindi mag-hold itong mga theorems na to. Tapos alam natin yung boundedness ay hindi enough para makapag-conclude ng integrability. Nakilala natin yung Dirichlet function. Remember, the Dirichlet function is the function f, that assigns to x the value 1 if x is a rational number and 0 if x is irrational. So this function is bounded because the values never exceed 1 nor they exceed 0. All right? Nandun lang siya sa either 0 or 1. Definitely bounded yan, pero hindi yan Riemann integrable. So kailangan may idagdag pa tayo dun sa boundedness para mag-guarantee na Riemann integrable ang isang function. When you go to graduate level real analysis, magde-define tayo kasi mapili tayo eh. Gusto natin yung mga bounded function kasi napaka-basic ng mga bounded functions. Bakit hindi natin sila kayang bigyan ng integral? So sa advanced calc, usually graduate level real analysis measure theory, you will define a much generic kind of integral that will allow bounded functions to be integrable in that particular sense. All right? Pero sa atin, meron pa sa undergraduate level, i-accept natin na hindi lahat ng bounded functions ay posibleng magkaroon ng integral, like the Dirichlet function. So sa graduate level nyo natitingnan, paano ko kaya babaliin yung definition ng integral o ng integrability para mapayagan na ito ay maging integrable. All right? But for us, let's accept the limitation of our theory kasi parang in-extend lang natin or pinapalalim lang natin yung understanding ng Math36 techniques na natutunan natin. Alright? So aside from boundedness, pag inimpose mo yung continuity ng isang function, automatically it's integrable. And then if the function is monotonic on the closed interval AB, then automatically integrable din siya. So monotonic, it's either increasing or decreasing. All right, so we did write a proof there. Okay, and then we can say by example 5.7 na madali lang nating makita na integrable yung mga function like yung mga polynomial functions, all right? Or actually, yeah, polynomials in general because polynomials are continuous on any closed interval. Therefore, by Theorem 5.2, pwede nating masabi na sila ay integrable na kasi continuous lahat ng polynomials. Also, the trigonometric functions, exponential functions, and even compositions of continuous functions are also integrable, right? Tapos, hindi necessary na continuous ang isang function para maging integrable. Pag bounded plus continuous, ibig sabihin siya ay automatically integrable. Pero kapag ka siya ay discontinuous, may chance pa rin na maging integrable siya. Katulad nitong floor function ni x. So, kukunin mo lang yung greatest integer less than or equal to x. So, parang nag-round down ka greatest integer of say 1.01, round down. Kukunin mo yung pinakamalaking integer na mas maliit kaysa kay 1.01. So ito ay 1, ang least integer ng 1 ay 1, least integer ng 0.99 ay 0, and so on. At kung makikita nyo, ang least integer function ay monotonic increasing all throughout any given interval. So, although it is discontinuous, lalo na kung merong integer dun sa gitna nung closed interval mo, hindi automatic na hindi siya integrable. Actually, it is integrable because it is monotonic. So that's one thing that we now learn. Hindi lang pala mga continuous functions ang posibleng maging integrable. May mga discontinuous function such as the step function or the least integer function that is discontinuous but Riemann integrable. And that will lead us to think, oh, so kung ganun, merong mga functions na discontinuous pero integrable. Tapos meron din naman mga functions like the Dirichlet function na bounded nga pero discontinuous naman pero hindi sila integrable. So that will lead us to the question of ano yung requirements sa continuity or discontinuity for that matter para maging integrable ang isang function. Ano yung limitasyon or ano yung pwede nating i-check kung meron kang discontinuous function, kailan yun magiging integrable? Kailan siya magiging katulad ng floor function o ng greatest integer function that is discontinuous but integrable? Or kailan siya magiging katulad ng Dirichlet function which is bounded but discontinuous tapos hindi naman integrable? And the answer there would be the Lebesgue integrability criterion. Pero we can take a look at a more subtle version of Lebesgue's integrability criterion, which is embedded in Theorem 5.3. Now, Theorem 5.3 tells us we'll still start with a bounded function, all right? And then we will assume that f is continuous on the closed interval AB except for a finite number of points. And then that will mean f is integrable, right? So, ito pala yung pwedeng exemption o ito yung pwede nating maging criteria para ma-check yung mga discontinuous functions kung sila ay integrable or hindi. Kapag ka finite lamang yung number of points kung saan sila ay hindi continuous, then f is still integrable. Pero kapag ka infinitely many yung mga points kung saan siya ay hindi integrable, then that's another question. We don't know if the function will still be continuous or not. All right? Now, we'll start with a proof of 5.3. Ito yung kinailangan kong i-edit dun sa final version ng lecture notes. So for those who came in late, nag-upload ako ng bagong version ng lecture notes around 7 minutes before 4. So may mga final edits akong ginawa, specifically sa proof ng Theorem 5.3 and some of the other proofs that you will see. So yeah, kindly download it before you actually before the next problem set para kompleto na yung set of notes nyo. Okay, let's read the proof. Or ito pala isang advice. what I noticed about the problem set submissions, specifically this last problem sets, uh, I think siguro 90% sure ako, most of you consulted other materials, be it some other books, be it some resources from the internet. Some of you cited Math Exchange, all right? The only merong isang danger yung paggawa nun. Yon ay yung conventions na ina-adapt. So whenever you're reading proofs online or in textbooks, right, kailangan nyo tingnan or kailangan nyo pa rin i-analyze yung bawat argument na nandun sa proof. Kasi baka yung mga proofs nila ay gumamit ng ibang theorems o ng ibang mga conventions o terms na hindi naman natin dinefine sa klase natin. So pag ganun yung nangyayari, I have no choice but to give you deductions, sometimes large deductions, kasi gumamit kayo ng isang concept or isang theorem o isang result na hindi ko naman pinakita sa klase or hindi natin pinrove sa klase. Yun nga lang, yung reference nyo siguro, pinrove siya before or inassume na totoo siya talaga following some other discussions. Pero ang basihan ko ay yung lecture notes. So, kaya siguro yung iba nagkaroon ng deduction. So, just be careful with that, even if, or even for future classes. So, take note of the conventions na ginagamit ng iba yung materials. So, I think that's one danger or one thing that you need to be wary about whenever consulting outside materials. But again, consulting outside materials is at least for me, is acceptable, and actually I encourage it pag talagang na-stuck na kayo sa isang particular problem. Pero yun nga, tandaan niyo yung caveat na yun para maiwasan niyo yung malalaking deductions. Alright? Okay, let's go over the proof of 5.3. Siguro ngayon, dahil medyo naghahabol na ako sa oras at saka um, gusto kong matutunan nyo paano magbasa ng proof. I will just go over the proofs written on the text rather than writing it from scratch na ginagawa natin dati. Tingnan natin step by step paano ginawa yung proof, tapos i-supply natin verbally yung mga detalye na hindi na nakasulat dun sa proof. Alright? Para rin masanay kayo how to read the other person's proofs. Okay? Saka medyo komplikado na kasi yung mga proofs. Maraming mga inequalities na bigla na lang sumusulpot, and mahina ako sa memorization. So it will take a lot of time for me to derive everything from scratch. Tapos hindi ko naman sila masasaulo ng mabilisan. So kaya kailangan may script talaga ako na susundin. Kasi susupply ko na lang yung mga details or yung ibang mga comments all throughout the proofs. Okay, I hope that's fine with you guys. Okay, so let's go to the proof of 5.3. So si f ay bounded. So ibig sabihin dahil si f ay bounded, may mag-exist na positive number m such that the absolute value of x will be less than or equal to m for all x in the closed interval AB. So nagamit na kagad natin yung requirement na si f ay bounded. Tapos, remember we assume that f is discontinuous only at a finite number of points, say capital N number of points on the closed interval AB. So si capital N, siya yung kung ilan yung mga points of discontinuity ni F dun sa closed interval AB. Then if we will be given an epsilon greater than 0, and perhaps this is a clue for you that the proof will try to apply the integrability criterion na bibigyan tayo ng challenge epsilon, maghahanap tayo ng partition inducer such that the upper Riemann sum minus the lower Riemann sum will be less than that epsilon. So yun yung pinaka-goal ng proof na to. Kaya meron diyang sumulpot na epsilon. Tapos, kailangan ko ng partition inducer. Ang gagamitin ko dun sa partition inducer ay magiging depende dun sa mga points of discontinuity, which luckily for us is finite. Tapos I'll do it in a clever way. Paano ko i-define yung mga yung partition inducer that will be my response to the given epsilon. Una, kukomputing ko si delta. Sino si delta? Siya yung pinakamaliit among these numbers. All right? It is the minimum of the following numbers. epsilon over 8 times capital M times N. At dito mapapawaw ka na lang. Bakit out of nowhere, nagkaroon ng epsilon over 8 times the upper bound times the number of discontinuities? Alright, so makikita natin yan mamaya. Bakit siya biglang sumulpot dyan? Probably the inequality that we'll get later para sa upper minus lower sum ay merong epsilon, merong 8 mn sa numerator or something like that. Kaya meron diyang epsilon over 8 mn. And the fact that we have capital N discontinuity points allowed us to define this fraction over here. Pag si n hindi na finite o hindi na siya natural na kung hindi na siya finite, hindi na mag-work itong proof na to kasi naka-ankla yung proof sa pagiging finite value ni n, kaya na-define itong fraction na ito. Tapos yung boundedness ganun din kasi yung upper bound para kay f played a major role in the definition of epsilon. Okay? Tapos, yung ibang mga numbers dito is the distance, or actually, it is a number depending on the distance of the points of discontinuity from each other and from the boundaries A and B. So, kung titingnan natin yung closed interval AB, okay, tapos meron ng points of discontinuity yung function, say kay Z1, kay Z2, kay Z3, kay Z4, and so on, hanggang kay Z subcapital N. Alright? Tingnan niyo yung mga numbers dito, Z1 minus A over 3. So titingnan natin gaano kalayo si A mula kay Z1. So ito yung Z1 minus A. Tapos i-divide ko ng 3. So ibig sabihin yung distance na yon ay hindi lalampas doon sa value ni A. So posibleng nandito yon. Ito yung Z1, etong haba na to, posibleng siya yung Z1 minus A all over 3. Para hindi ako lumampas dun sa kabilang interval. Tapos, ganun din yung mga susunod. Kaya lang, hindi siya lalampas dun sa previous point of discontinuity. Yung Z2 minus Z1 over 3, yun yung layo ni Z1 mula kay Z2, pero i-divide ko ng 3. So, ibig sabihin, mas maiksi yan. Ito yung Z2 minus Z1 all over 3. That would be somewhere there. Basta ang usapan, hindi siya lalampas doon sa susunod na point of discontinuity. So, ang idea rito ay, parang kinukulong ko bawat point of discontinuity sa isang mas maliit na interval. Alright? Kasi yung delta, pinipili ko siya to be the smallest among this n plus 1 guys over here. So, ibig sabihin, ginagaranti ko na yung delta ay hindi lalaki doon sa distance between two consecutive points of discontinuities as well as this number, this magic number, epsilon over 8 mn. So kung titingnan ko si delta, posibleng pag si delta yung ginamit ko, as yung delta, siya yung gagamitin kong haba or half the distance or radius ng mga intervals kung saan ko kukulungin yung mga points of discontinuity. So, pwede nating isipin ito ay delta units, tapos ito ay delta units din, and so on. So, nakakulong yung mga points of discontinuities sa mas maliliit na intervals. So, yung mga intervals kung saan sila nakakulong, sila yung tatawagin nating mga intervals of this form. Yung union ng mga intervals C1 minus delta, comma Z1 plus delta, right? Sila yung yung union ang tatawagin nating P sub 0. Alright? So kukulayan ko ngayon yung P sub 0 by pink highlights over here. Okay? Parang sila yung mga red flags. Kasi dyan, hindi natin ma-define yung Riemann integral right away because the function is discontinuous on these pink intervals. Kaya dito kayon kay P sub 0. Alright? So again, ang idea nitong delta, makulong yung mga points of discontinuity sa mga mas maliliit na intervals. Alright? And the result of that is, outside of those smaller intervals, yung function natin ay magiging integrable na. Kasi for instance, on the interval A to here, which is Z1 minus delta, continuous yung function. Therefore, it is integrable by Theorem 5.2.1. So dito sa yellow, integrable yung function. Okay? Likewise, between z1 plus delta and z2 minus delta, continuous yung function, therefore differentiable, and so on. Okay? So, dun sa mga yellow intervals, yung function naman natin ay integrable na. So, tawagin natin tong E1, tawagin natin tong E2, tawagin natin tong E3, and so on. Tapos, alright, good so far? So, yun yung idea nung delta. So, makikita natin, paano ko kaya to gagawin? I will appeal to the sort of, what do you call this? Dadayain ko ng konti, gagamit ako ng additivity ng integral. Pero dahil hindi pa na natin na-prove yung additivity ng integral, medyo kailangan kong itago yung argument sa language na nagamit na natin before o yung mga results na nagamit na natin before. In particular, since the function f is integrable on each of the e sub i's, then there will exist a partition inducer p sub I of e sub I. So, di ba, yung integrability criterion. Pag integrable yung function, may mahanap ka na partition inducer such that the upper minus the lower sum will be less than an arbitrary number epsilon. Okay? So, dahil integrable na siya sa mga e sub i's, sa bawat e sub I, may makukuha akong partition inducer pi such that the upper Riemann sum minus the lower Riemann sum will be less than an arbitrarily small positive number. And I will choose that positive number, that arbitrarily small positive real number, to be epsilon over 2 times n plus 1. Tapos, wow na naman dito. Kasi, saan nanggaling yung epsilon over 2 times n plus 1? Makikita natin yan later. Okay? Kung nagsusulat kayo ng proof from scratch, usually yung ginagawa ko lang yung mga beta, tapos ito, gagawin ko yung halimbawa na gamma, tapos tapos i-work out ko yung math, tapos pag nakita ko na yung final inequality, halimbawa yung nakuha kong final inequality ay 8 epsilon or 8 beta. So alam ko na yung beta rito dapat maging epsilon over 8 para ma-simplify yung final inequality to be less than epsilon. So kind of working backwards, pero the lecture notes had the luxury of computing everything beforehand, kaya alam niya na kailangan etong beta na to ay maging epsilon over 2n plus 1 para sa final simplification ko later, epsilon yung lalabas. Alright, so yun yung mga tipo ng pandaraya sa mga mathematical proofs, especially in analysis. So kaya parang mapapahanga ka na lang na, okay, what the blank that happened, kaya nakuha niya yung epsilon over 2n plus 1 dito. Alright? Now, ang concern natin ay mapakita ito sa buong interval AB. Ang inequality na to ay napakita natin sa bawat e sub i's. Sa bawat e sub i's, nakakuha tayo ng partition inducer na p sub I. Para mapakita na integrable si function f sa buong interval AB, dapat ay magawa natin ito or makakuha tayo ng version ng inequality na to that will work for the entire interval AB. Our problem was, eto mga pink intervals na yan. That disallowed us from getting to the desired inequality right away. Pero susolusyonan natin yan ng konti. So labanan ng partition inducers. So meron ng issue na challenge or na challenge na epsilon. Kailangan natin mag-construct ng partition inducer sa buong interval AB. Now I'll start doing that. So si E, tatawagin ko lang siyang union ng mga yellow intervals. So E is the union of E1, E2, E3 until E sub n plus 1. Tapos si P, yung target partition inducer ko na sasagot dun sa challenge na epsilon. Sasabihin ko siya ay si E. Mali pala yung ginamit ko na E. Dapat partition inducers dapat kay E. So dapat si P ay ganito yung itsura niya. Yung mga partition inducers para sa mga E sub I. So ito ay si A. Tapos dapat si Z1 minus delta. Tapos si kasi ito yon.
yung boundary ni E1. Tapos yung boundary ni E2 ay Z1 plus delta, comma hanggang dito. Siya ay magiging Z2 minus delta, and so on. Okay. Tapos, oh yeah, so I guess ito ay hindi E, dapat ito ay close set containing AB. Right, I think that is fine. So meron akong set containing A, B, union, yung mga boundaries. Ito yung sagot na partition inducers para dun sa challenge ni epsilon. Yun yung ipapakita natin. So ang partition inducer ko ngayon kinoconsider si capital P consists of the boundaries of the intervals E sub i's. Okay? So ipapakita ko na yung sum ay yung upper Riemann sum minus lower Riemann sum corresponding to this partition inducer P, which consists of the boundary points of the E sub i's, will be less than epsilon. Okay? Yun yung gusto nating ipakita. And I just renamed this guys, yung laman niya, to be the T sub i's. Para lang mas madali natin siyang maisulat. So, i-arrange ko lang yung elements na to as the T sub i's. So, ito si T sub 0, ito si T sub 1, ito si T sub 2, ito si T sub 3, and so on. Para lang mas madali silang i-track para hindi ko na kailangan gamitin yung delta kasi nagpa-plus or minus tayo ng delta. Alright? So, it's just a renaming of those partition inducers. So, compute natin yung upper minus lower sum. Gusto ko mapakita na ito ay less than epsilon. But remember, when we expand this will just be the sum of the supremum over the subinterval minus the infimum function value over the interval times the length of the particular interval. So, yun yung formula para sa upper minus lower Riemann sum. Okay. And then, what we know is that the T sub i's is either, or this interval, is either contained in P sub 0 or in E. Kasi ito si T sub, remember, ito si T sub 0, ito si T sub 1, ito si T sub 3, ito si T sub 4, ito si T sub 5, T sub 6, and so on. So pag kumuha ko ng T sub I minus 1, comma T sub I, it's either a yellow interval or a pink interval. So dalawa lang yung options. Yellow or pink interval siya. So ibig sabihin, etong sum na to, all right, over the partition P that we have chosen according to the yellow and the pink intervals ay equal dito. Pwede ko siyang i-separate sa dalawa. Una, yung upper minus lower sum dun sa mga induced partitions na nandun sa pink intervals. So ito yung isa sa mga pink intervals. Tapos ito, isa naman siya dun sa mga yellow intervals. Okay, so ito yung corresponding sa pink intervals. Kung saan yung function ay discontinuous. Ito naman yung para sa yellow intervals. Kung saan yung function alam natin ay continuous and hence integrable. Okay? Tapos, ang mi minus mi, sila yung mga differences ng mga suprema at mga infima. Pero definitely, mi minus capital Mi minus little mi will be less than 2 times the suprema over the supremum over the closed interval AB. So kung ko-computing ko yan, ang mi minus mi will be less than or equal sa mi minus mi. Actually, equal pala yan. Kasi yung capital MI, pinakamalaki siya. Little mi ay pinakamaliit. So this is positive. I will apply the triangle inequality dun sa absolute value. Okay. Alright. Tapos, gagamitin ko yung pagiging upper bound ni capital M. So lahat ng function values ay less than capital M. So kaya siya naging 2M. So kaya ito dapat less than. So this is one of the corrections I made with the previous version of the lecture notes. Para naka-equate siya, I think it should be less than or equal to. So, yon. Etong difference na to naging 2M. Tapos yung T1 minus T sub I minus 1, okay, that will be this length, all right? And that would be bounded by delta. Okay. So kaya siya naging, or actually twice delta. Kasi ito ay twice delta yung laman. So that would be twice delta over there. And then ito, pwede ko siyang isulat as this guy. Kasi ito ay, yeah, very definition ng upper minus lower Riemann sum over the interval. Okay? Now, this, simplifying this, we'll get 4mn delta. Lalabas yung 4. 2 times 2, lalabas 4. Lalabas si m kasi constant siya. Lalabas si delta kasi constant siya. So this would be 4m delta times the sum of 1s, I going from 1 until capital N. So kaya nagkaroon ng capital N na factor over there. Right? So yun yung first sum natin. Plus, the second sum will be this guy. Pero ito ay upper minus lower Riemann sum for every partition inducer of the E sub i's. Pero dahil alam na natin kanina na yung upper minus lower sum sa bawat partition inducer ni E sub I ay mas maliit sa epsilon over 2 times n plus 1. So kaya ito, mapapalitan ng epsilon over 2 times n plus 1. Okay? And then here, so this guy, remember delta was chosen to be the minimum among those long list of numbers before, but we know definitely that delta is less than epsilon over 8mn. So itong delta rito, pinalitan ng 8 over epsilon mn, kaya naging epsilon over 2 na lamang siya. Tapos ito ay yung sum na yan will be less than epsilon over 2 as well. So parang anong ginamit doon? Kinuha lang yung sum formula. So in-evaluate itong sum na to. And I think that is less than epsilon over 2. Tapos, epsilon over 2 plus epsilon over 2 equal na siya kay epsilon. So what we have found here is that given any epsilon greater than 0, pag kinuha ko yung upper minus lower Riemann sum, nung partition inducer so constructed, specifically constructed for that epsilon, because the partition inducer P is dependent on the choice of delta, and in turn, that choice for delta is dependent on epsilon, the bound for the function f, and the number of discontinuity points. Napakita natin na itong difference na to ay laging less than epsilon. And so by the integrability criterion, Theorem 5.1, the function f is integrable even though it has a finite number of discontinuity points. All right, so that ends our proof. Okay. So Math 36, medyo ginagamit na natin tong idea na to, na kapag finite yung discontinuity points, ang ginagawa natin, hinahati natin yung interval into several pieces. So kung siya ay discontinuous sa Z1, tapos gusto natin siyang i-integrate, kukunin ko yung integral mula kay A hanggang kay Z1. Posibleng improper yung integral kay Z1, idadagdag ko siya sa integral from Z1 to Z2, which could possibly be also an improper integral. But if our function is so nicely behaved over those subintervals, the improper integral will converge. Kaya nadadaya natin siya kapag finite yung number of discontinuity. From the pragmatic point of view, hinati-hati natin siya and we appeal to the additivity of integrals. Pero the idea why we can do that is through this partition inducer or this special partition inducer for the closed interval AB. All right? So now, pwede nyo na itong idagdag sa list of integrability criteria. Alam na natin pag si f ay bounded at continuous, siya ay automatically integrable. Ngayon, idadagdag natin pag siya ay bounded, tapos discontinuous lang siya sa finite number of points, then siya pa rin ay integrable. Now, there's a quick proof for the other case not covered by this theorem. Paano pag infinitely many yung point of discontinuity? So the idea there is kapag infinite yung point of discontinuity, that's still a question, all right? Pero meron na tayong at least isang point, isang function na alam natin na may infinitely many points of discontinuity pero hindi siya integrable. Yun yung Dirichlet function natin kanina, right? Now, para ma-stretch natin yung integrability criterion, kasi alam na natin pag finite, paano pag infinite yung number of points of discontinuity? Posible pa rin ba siyang maging integrable? So, kailan siya integrable, kailan siya hindi? To better understand this concept, tingnan natin yung set of measure zero. What does it take for a set to have a measure equal to zero? So if you have a subset A of the set of real numbers, tatawagin natin siyang set of measure zero if sa kahit anong epsilon greater than zero, there exists a countable, so crucial yung countability, no collection of open intervals such that the set A is a subset of the union of these open intervals or discountable open intervals, and the sum of the lengths of these subintervals is less than or equal to epsilon. So, ibig sabihin, siya ay set na measure zero kapag kaya nating ikulong yung buong set A sa union ng mga closed intervals na ang length yung sum ng lengths ng mga subintervals na yon sa union ay mas maliit kay epsilon. So, parang ang idea rito ay, halimbawa, ang set A ko ay itong mga dots na to. Okay. For instance, I have a countable or I have a finite number of points in my set. So, halimbawa, ang set ko ay si set containing A1, A2, A3, A4, A5 until A6. Then, mapapakita ko to ay isang set of measure zero kasi kaya kong, pag binigyan ako ng epsilon, okay, ng kahit anong epsilon, kaya kong ikulong etong finite set na to into a union or inside a union of closed intervals whose length is equal to epsilon. So, ilan nga ba to? So, meron akong 6 na points of discontinuity. Pag binigyan ako ng epsilon, i-consider ko yung epsilon over 6. Kunin ko yung interval of length epsilon over 6. Actually, dapat pala, ito ay epsilon over 12, sa kanan epsilon over 12, para yung total length niya ay epsilon over 6. Ito, si A2, ikukulong ko siya sa A2 minus epsilon over 12 hanggang kay A2 plus epsilon over 12. So A2 minus epsilon over 12, A2 plus epsilon over 12. So yung haba ng second interval, O sub 2, yung pangkulong na interval, ay epsilon over 6. And I can do that accordingly to the remaining 4. So bawat pangkulong na open interval ay length na epsilon over 6. Kailangan ko lang ng 6 na pangkulong para masatisfy yung definition na to. Right? So ibig sabihin, this is a set of measure zero. Actually, any finite set has measure zero. And that is what was given. Yan pala yung sinasabi ng example 5.8. Kahit anong finite, measure zero siya. Right? Tapos, meron din mga infinite sets na measure zero pa rin. In particular, any countable set has measure zero. Do you guys remember ano yung ibig sabihin ng countability? Kailan countable ang isang set? Tandaan niyo pa ba from math, kailan ba? 101? Ang isang set ay countable kapag siya ay equivalent o kasing dami or kasing laki ng set of natural numbers. So if you can put your set in a one-to-one correspondence with a set of natural numbers, then that set is countable. So kaya siya sabing countable kasi kaya mo siyang bilangin, hindi nga lang natin sure kung matatapos ka sa pagbibilang. Alright? So yung set of natural numbers, kaya mo yung bilangin, pero hindi ka matatapos ever. Yung set of rational numbers, hindi siya countable. Hindi. Set of rational numbers ay countable. Kasi yung diagonalization technique, kaya mong bilangin lahat ng fractions. Pero yung set of irrational, set of real numbers, hindi sila countable. Kasi halimbawa, mag-start ako kay 0. Sino yung susunod na real number kay 0? Hindi natin alam. So there's no way to count them in a systematic way. So ang irrationals at ang mga reals ay examples ng non-countable sets. Pero all others are countable sets. Okay? Now, sabi ng example 5.9, a countable set has a measure 0. Okay? Tapos yung proof, ginalingan niya lang yung pili ng mga pangkulong na interval. Kung kanina, ang pinili kong pangkulong na interval would be of length epsilon over n. Right? Kung meron akong n na ikukulong, mag-aalat ako ng epsilon over n na pangkulong sa bawat element ng set. Kapag pagka infinite na yung mga elements ng set na kailangan kong ikulong, ang gagamitin kong length ng interval ay ito. Epsilon over 2 to the power n plus 1. Alright, so ito yung gagamitin kong mga capital O's. Now, clearly, mako-cover niya lahat ng mga a-sabays kasi nasa loob sila ng mga intervals na to. So definitely, my set E will be a subset of the union of these intervals. So nakakulong pa rin sila dun sa mga open intervals na to. Bawat isang element ni E, merong isang interval kung saan siya nakakulong. Tapos, pag kinuha ko yung summation ng mga lengths ng mga intervals na to, I have a countable number of such intervals kasi countable yung set na to. Infinitely many but countable. So meron akong countable open intervals. Bawat isa sa kanila ang haba ay epsilon over 2 to the power n plus 1. Okay? Now, geometric series or geometric sum, isi-simplify ko ito, ang sum niya ay epsilon over 2, which is still less than epsilon. So meaning, if we have a countable set, we can define our open intervals. Ang tawag nga pala dito ay mga covers. Yung pang-cover natin dun sa set E, bawat isa sa component niya ay may length epsilon over 2 to the power n. So sobrang liliit ng mga O sub n's, alright? Pero essentially, even countably many sila or countably infinite many sila, ang sum pa rin ng mga lengths ay epsilon over 2 less than the challenge epsilon before. So any countable set has measure 0. All right? Now, here comes the nice result due to Lebesgue, which is actually, I think, the most generic integrability criteria, at least for our course. And actually, hindi nga lang eh. I think kahit sa advanced calculus, advanced calculus nga pala tayo, no? Pero sa graduate level calculus, ito pa rin na isa sa mga fundamental results, yung Lebesgue's criterion for Riemann integrability. And it says that if we have a bounded function on the interval AB, then f is integrable if and only if the set of points where f is not continuous has measure 0. So parang generalize niya yung result natin kanina, yung Theorem 5.3 natin kanina. Yung Theorem 5.3 natin, sabi ay kapag ka finite yung points of discontinuity, siya ay Riemann integrable. Okay? Pero sabi nga, may mga functions like the integer, the floor function, the greatest integer function, discontinuous pa rin siya pero integrable siya. The reason there is that it is not very discontinuous. It is discontinuous only at a finite number of points on a given closed interval. So dahil finite yung number of discontinuity niya, actually, finite nga ba? Yeah, finite. Pero mas gusto natin, mas generic to. Dapat siya ay countable. Pwedeng maging at most countable or countably infinite yung number of points kung saan siya hindi continuous. Pag yun ay nangyari, automatic siya pa rin ay continuous. Siya pa rin ay Riemann integrable. Kasi sabi ni Lebesgue, nung Lebesgue criterion, kapag ka ang points where f is not continuous has measure 0. Example of which are finite sets and countable sets. All right? Pero meron pa mga ibang sets of measure 0, but you will need measure theory, which is discussed in Math 230. Sa kanyo titingnan ano pa yung mga sets na measure 0 aside from finite and countable sets. Pero for now, alam na natin na kapag ka finitely many lang or countably many lang yung points of discontinuity, then the function is still integrable. Okay? Now, babalikan natin yung Dirichlet function. Yung Dirichlet function uli natin ay f of x equals 1 if x is rational, and it is 0 if x is irrational, right? Actually, this function is discontinuous everywhere. It is bounded, but it has infinitely many points of discontinuity. At yung number of, tapos yung points of discontinuity niya ay hindi of measure 0. Right? Hindi measure 0 yan kasi kahit i-define mo to sa 0, 1, so i-restrict natin yan sa 0, 1. Okay. Ang points of discontinuity pa rin niya will have measure 1. Kasi ang measure ng isang closed interval ay yung haba ng closed interval. The function f, defined this way, will be discontinuous at all numbers on the closed interval 0, 1. Kasi wala kang mahanap na point of continuity niya sa buong closed interval 0, 1. Yung closed interval 0, 1 is measure 1. Kasi ang haba ng interval ay 1. So hindi siya measure 0. So this guy, even though this is bounded, will not be Riemann integrable. Okay? So kailangan either finite, discrete, or countably infinite, or generally dapat measure 0 para maging Riemann integrable ang isang bounded function. All right? Now we have developed a good theory about integrability. The next question is, how do we evaluate, or is there a neat way of evaluating the Riemann integral for a function without going through the process of collecting all Riemann sums, getting the infimum and the supremum, and comparing those two values? Now, the theorem that we will use there is what we call the Archimedes Riemann theorem. Let me see if I will prove this. Sige, daanan natin yung proof ng Riemann, ng Archimedes Riemann theorem. The Archimedes Riemann theorem tries to connect integrability with limits of sequences. All right? Ano yung sequence na ginagamit natin pang evaluate dito? Kumukuha tayo ng sequence ng partition inducers. Tapos kukunin natin, titingnan natin yung limit ng sequence formed by the differences of the upper and the lower Riemann sums of those partition inducers. And if the difference will converge to 0, then we say that the function is Riemann integrable. And it's an if and only if statement. So magbuo ka ng isang sequence ng mga partition inducers. Okay? Pag may nakita kang sequence of such partition inducers such that the limit of the sequence formed by the difference of the upper and the lower Riemann sums corresponding to the elements of the partition inducers converges to 0, then f is Riemann integrable. And not just that, the integral of f on the closed interval will be equal to either the limit of the upper or the lower Riemann sum. Okay? So pagka pala sure ka na integrable yung isang function, kunin mo lang or bumuo ka lang ng sequence of partition inducers, kunin mo yung limit ng upper sum niya, then that will give you the desired integral. Similarly, you can use the lower sum instead. Okay? So let's briefly look at the proof. It's an if and only if statement with a bonus here. So umpisa natin, i-prove natin yung if and only if statement. Now for the forward part, we will assume that f is integrable. And we want to show that this limit statement is true. Okay. Now, if we will assume that f is integrable on the closed interval AB, then by the integrability criterion, kahit bigyan tayo ng kahit anong epsilon, halimbawa, piliin ko yung mga epsilon na 1 over n, then para sa bawat isang 1 over n, alright, sa bawat isang epsilon sub n, may makikita kong partition P sub n ni closed interval AB. Actually, this should be a partition inducer of AB such that totoo ito or totoo itong inequalities na to. Alright? So, Theorem 5.1 yung ginamit ko rito. Bigyan ako ng epsilon. May mahanap ako ng partition inducer such that the difference would be less than the chosen epsilon. Okay? So, ang pinili kong epsilon sub n ay 1 over n. Alright? Tapos, alam ko na yung upper ay laging mas malaki sa lower Riemann sum. So, I can include that 0 on the left side. Tapos, gagamitin ko yung napaka-powerful na squeeze theorem. Kukunin ko yung limit nito, limit nito, limit na to. And that's why I chose epsilon sub n to be equal to 1 over n. Kasi yung limit ng 0 ay 0. Yung limit ng sequence na 1 over n ay equal kay 0. So limit nito ay 0, limit nito ay 0. Sabi ng squeeze theorem, yung limit nung nasa gitna ay equal dun sa limit nung nasa magkabilang dulo. So the limit of this guy is equal to 0. And that proves the forward part. Okay? Now, yung converse naman. I-assume naman natin na may nag-exist na partition inducer P sub n such that the limit of this difference is equal to 0. Tapos gusto kong ipakita si f ay Riemann integrable. Gagamitin ko rin si Theorem 5.1. Okay? Kaya lang, ang alam ko, ito ay nagko-converge kay 0. So gagamitin ko yung definition ng limit ng isang sequence. So sa bawat epsilon greater than 0, may nag-exist na capital N in N such that for all little n greater than or equal to capital N, we have this guy is true. Alright? So in-apply natin yung definition ng limit ng isang sequence. Right? Supposedly may minus 0 ka pa dyan kasi yung limit ng sequence ay 0. Pero hindi na natin siya nilagay, sinimplify ko na kagad. In particular, we know that this guy is less than epsilon, which is basically what is required by the Integrability Criterion Theorem 5.1. So alam natin, sa kahit anong ibigay na epsilon, lagi ako may mahanap na P sub capital N. May isang partition inducer. Actually, napakaraming partition inducers ngayon mahanap ko simula kay P sub capital N pataas. P sub capital N plus 1, P sub capital N plus 2. Lahat sila ay mag-work as a partition inducer whose upper and lower Riemann sums are arbitrarily close to each other. Or actually, the upper and the lower sum is within epsilon distance from each other. And thus, we just need to appeal to Theorem 5.1, and we will get f is integrable on the closed interval AB. Okay? So, yun. Tapos na yung if and only statement. So, parang nirephrase natin yung Theorem 5.1 into more familiar terms. Dito ay in the language of limits of sequences. Okay? Kasi prove natin yung bonus statement. Ano yung bonus statement? Kapag kasi f ay integrable, automatic daw ito ay totoo. Yung Riemann integral ay equal sa limit ng upper sums with respect to partition inducers P sub n as n approaches positive infinity. Okay? So, paano siya nangyayari? Kung si f ay integrable, may mahanap tayong sequence of partition inducers such that this limit is true. Alright? Or this limit statement is true. Tapos, kung totoo yan, ang limit niya ay 0, ibig sabihin, pwede ko itong i-distribute yung limit sa loob ng dalawa na yan. Tapos gusto nating ipakita na yung limit, yung dalawang limits na yun na magkahiwalay ay nag-e-exist separately. Tapos, pag sinubtract ko sila mula sa isa't isa, sure tayo yung difference ay 0. And it is a coincidence that that limit, either of the two limits actually, would be equal to the Riemann integral. Remember, medyo kailangan ko maging careful dito. Kapag yung limit ng difference ay nag-exist, hindi ibig sabihin na nag-exist yung limit nung minuend at yung limit ng subtrahend. Posible nag-cancel out lang sila, pero individually, hindi nag-exist yung limits nila. So part yun ang gusto kong ipakita dun sa proof ng bonus statement o ng part B. Okay? Now, using the same epsilon as we have used above, okay? Now, sure ako na kasi si f ay integrable na nga, tapos sabi daw ay may nag-exist na partition inducer such that for all epsilon greater than 0, totoo itong nasaan ba yung inequality na yun? Theorem 5.1. Totoo dapat ito. Right? So that means for each one of this p sub little n's, totoo itong susunod na mga inequality. So carefully curated itong mga inequalities na gagamitin ko. Una, magsimula ako sa lower Riemann sum with respect to the partition inducer p sub n. Tapos, alam ko na yung lower Riemann sum ay siya yung supremum ng mga lower sums. So this guy is the least upper bound ng mga ito. So definitely, it is an upper bound first. So kaya totoo itong inequality na ito. Alright? But since we know that f is Riemann integrable, then the lower Riemann sum is equal to the upper Riemann sum. But what is the upper Riemann sum? The upper Riemann sum is the infimum of the upper sums. Oh, sorry. The upper Riemann integral is the infimum of the upper Riemann sums. So infimum siya yung greatest lower bound. So this guy is a lower bound for all of the upper sums. And hence this inequality over here. Okay? Pero, alam natin na totoo itong inequality na to kasi nga si f ay Riemann integrable. Right? So I can add the lower sum to both sides. So I will get the upper sum would be less than epsilon plus the lower sum. And that's what I get over here. But again, the lower Riemann sum, okay, is less than or equal to the lower Riemann integral. So, ito, papalitan ko lang nito, tas may naka-plus pa na epsilon. But again, f is Riemann integrable. So dahil si f ay Riemann integrable, so this guy would be less than, this guy will be equal to the actual integral plus epsilon. Actually, parang, teka, parang pinakomplikado ko yung buhay ko rito. Mukhang may shortcut. Yeah, nag-aksaya ako ng steps dito. Will you agree kung buburahin ko na lang ito? Mukhang pwede na siya, no? Si epsilon ay positive. So yung lower sum, pag dinagdagan ko ng positive number epsilon, totoo itong inequality na to. Tama, no? Pinaikot-ikot ko yung argument. Pwedeng wala na yata itong inequality na to. Ngayon ko lang na-realize. Let's see kung magkakaproblema ako pag binura ko yon. Tapos, ito yung sinasabi ko kanina. Yung lower Riemann sum ay upper bound para sa mga lower sums. Yung lower Riemann integral ay upper bound para sa mga lower sums. Kaya meron ako ditong inequality, yung L, pinaltan ko ng lower integral. Tapos, dahil si f ay integrable, yung lower integral equals siya dun sa Riemann integral. So essentially, what we have now is this guy is less than or equal to, or actually this guy is less than the integral of f plus epsilon. So meaning, ang layo or mula kay L, dadagdagan ko lang siya ng epsilon para, baliktad. Yung actual integral, pag dinagdagan ko ng epsilon, magiging mas malaki na siya sa lower Riemann sum. So, ibig sabihin, yung distansya sa pagitan ng lower sum at saka nung actual Riemann integral ay less than epsilon. And that's what I have over here. I see. I see kung bakit ko to dinagdag. Kasi kakailanganin ko siya dun sa second statement. Dun sa second statement naman, ito ay mas maliit kesa dito. So that means the upper Riemann sum is still within epsilon distance away from the Riemann integral. So pwede akong mag-subtract from both sides ng epsilon o ng integral of f, tapos makukuha ko less than epsilon pa rin. That's how I get this inequality. All right? But remember, the choice of epsilon here is arbitrary. So napakita natin na kahit anong epsilon pa yung ibigay, may capital N tayo na mahanap, which is the same capital N which I used in the second part of the earlier proof. All right? such that the lower Riemann sum or the element of the sequence of lower sums minus the Riemann integral will be less than that value of epsilon. So ibig sabihin, yung limit ng lower Riemann sums ay equals sa integral of f. And similarly, yung limit ng upper Riemann sums ay equals sa integral ni f over the interval AB. Okay? So this partition or this partition inducer is what we call the Archimedean sequence of partitions. Though it's a little bit, what to call it? Dapat wala yung star. It's a little bit of a mouthful to say Archimedean sequence of partition. So yeah, I don't usually use this term, but it's nice to know that we have such a term para makover yung mga partition o yung sequence of partitions that is created in pursuance to the Archimedes Riemann theorem. Okay? Now, let me see if I can... Okay. I think I can still continue. Konti na lang to, guys. Just bear with me. Regular partition. Anong ibig sabihin ng regular partition? Ang isang regular partition o isang regular partition inducer, okay? Dapat ito ay partition inducer. Regular partition inducer. Pag sinabi nating regular partition inducer, ibig sabihin magkakasing haba yung mga intervals. Meaning delta x sub I are all equal to b minus a over n. So pag regular yung partition inducer, yung partition na binibigay niya sa atin ay magkakasing haba yung mga open intervals. So its length would be b minus a all over n. Okay, so yun lang yung gusto niyang sabihin. Tapos, pwede nating i-define ano yung Riemann sum. In the notion of the Riemann sum that you know from Math 36. So meron tayong lower Riemann sum, upper Riemann sum kanina, or even before. Nang kinukuha nating function value ay yung supremum at saka yung minimum over the interval. So if we will not choose the maximum or the minimum to be the corresponding height na ilalagay natin dun sa pagko-compute ng area ng mga rectangles according to the regular partitioning, right? Then we will get a generic Riemann sum. Okay? So yung Riemann sum dapat ay meron kang regular partition ni P, tapos yung function value na ginagamit natin ay hindi necessarily yung maximum nor the minimum, but they are just arbitrary function values over the subinterval. Okay? So instead na maximum at minimum, ang pipiliin ko na function value to represent the subinterval would be an arbitrary function value. Right? So pag ganun, tatawagin lang natin siya simply to be a Riemann sum. But just be careful, I'm using the article A here kasi hindi unique yung Riemann sum with respect to a partition P. Kasi nakadepende siya dun sa pagpili mo ng mga C sub i's kung saan i-evaluate mo yung function doon sa interval x sub I minus 1 hanggang x sub I. Now with that being said, obviously, the function value f of c sub I, which we will use as the height of the rectangle on each of the subinterval, right? Siyempre, mas malaki yon or equal sa minimum. Tapos mas maliit or equal din siya dun sa maximum. Tapos i-multiply ko both sides dito ng x sub i's, which is a positive value, that's the length of the ith subinterval. Tapos kukunin ko yung summation, we will get this. The Riemann sum is always bounded below by the lower sum and bounded above by the upper sum. Okay? Now, we will end with Darboux's theorem. So siguro ito yung mas nakita natin sa Math 36, yung part A at saka C. Right? So sinasabi ng Darboux's theorem na equivalent itong tatlong statements na to. F is integrable, and then the limit of the difference between the upper and the lower Riemann sums is equal to 0, where P sub n is the nth regular partition of A comma B. Pero actually, we kind of seen the equivalence between A and B. Ito yung Theorem 5.3, sorry, anong theorem yun? Siya yung Archimedes-Riemann theorem, Theorem 5.5. Ang pinagkaiba lang nitong statement na to ay regular partition, yung P sub n. Yung Archimedes-Riemann theorem natin, hindi nire-require yung mga P sub n's to be regular partition inducers. Pero nag-work siya sa lahat ng klaseng partition inducer, so ibig sabihin mag-work siya sa lahat ng regular partition inducers din. So that means we're done proving the equivalence between A and B by just citing Theorem 5.5. Now the new thing that Darboux's theorem puts into the table is the next condition. Na yung limit ng mga Riemann sum, okay, ay equal dun sa integral ni f over the interval AB. Okay? So again, if f is integrable, then this limit statement is true. Theorem 5.5 proved this for the limit of the upper sum and the limit of the lower sum. Pero Darboux's theorem says, totoo rin yan kapag kinuha mo lang yung isang arbitrary Riemann sum. Okay? Now, to prove Darboux's theorem, kailangan nating i-prove na A if and only if B. Tapos, so A if and only if B. And this is already done. So it is just sufficient to show that B is equivalent to C. So if we will be able to do this, then we can conclude that the three statements are equivalent. Because this will also imply that A, if and only if C, by transitivity of the conditional statement or biconditional statement. So parang anong tawag sa kanya sa 101? Siya yung hypothetical syllogism applied both ways. So reading assignment na lang, nandito naman yung proof ng B if and only if C. Kailangan yung i-prove na B implies C at saka C implies B. Tapos makukompleto na yung proof ng Darboux's theorem. And I guess this is what we used in Math 36 pag-define ng area nung region bounded above by a curve F and below by the x-axis. So kinuha natin yung upper sum, lower sum, saka yung midpoint. Pero mayroon tayong sinasabi na remark to na actually yung choice mo ng pang-evaluate ay hindi material. Kasi pinapaliit lang naman natin yung lengths ng mga subintervals. So essentially, parang nagiging random draw na siya ng isang element nung isang subinterval. So that's what Darboux's theorem is trying to formalize here. And then, yeah, as I've mentioned, the reading assignment na lang siya dito. And then we'll have Theorem 5.5, which is basically what I said before. If f is integrable, we know from the Archimedes-Riemann theorem that this is true, that the integral is equal to the limit of the lower sums. And thanks to Darboux's theorem, we also know that the integral is equal to the limit of the Riemann sum, and therefore we have this very long equation here. Okay? So I think I can stop here. So tingnan natin ano yung natitira for Thursday. So probably I'll illustrate the use of Darboux's theorem via examples 11 and 12. Medyo marami pa pala. Meron pang properties ng Riemann integral, mean value theorem, saka fundamental theorem of calculus. So I doubt kung matatapos ko siya sa Thursday. Pero if that's the case, then kung di natin siya matapos sa Thursday, magmi-meet na lang tayo Tuesday next week. That would be the 21st. But in either case, I will give you the problem set on Friday para masimulan nyo na. Ang coverage ng problem set na yon ay mula sa... Ano nga yung coverage ng huli nating problem set? Ang bilis ko makalimot, no? Siya ay about continuity, if I'm not mistaken. So ibig sabihin yung last problem set natin is about differentiability or differentiation and integration. So what I'll do is to give you siguro 3 questions na lang. First question is an essay writing contest or essay writing problem consisting of 5 questions. The second problem will be proving exercise involving derivatives. Tapos yung third problem would be a proving problem involving integrals. So, ganun na lang yung gagawin ko para 3 problems lang yung sasagutan nyo ulit. Alright? And then once I give it to you on Friday, you can start answering questions 1 and 2. Tapos posible yung question number 3, kailanganin pa natin yung result natin for Tuesday next week. So I hope that's fine with you. Do you have any questions? Sorry, medyo halata niyo nagmamadali ako, no? So nakalimutan ko mag-pause to ask for if you have some questions. But yeah, we can devote the last 3 minutes for questions, clarifications, or whatever. Gusto niyo mag-comment or something. Parang patapos na yung SEM. Baka hindi ko pa naririnig yung mga boses nyo, no? So, yun. Yun pala, yung mga nag-recite, wala pa yung maliit na bonus points. Emphasis on maliliit na bonus points dun sa mga pag-recite nyo. So, hindi ko pa siya nabibilang kay team. So, hopefully magawa ko na siya over the Christmas break. So, yung standing nyo ngayon, yan yung minimum. Kasi wala pa yung mga maliliit na bonuses for recitation. Okay? So, do you have any concerns, guys? Sure, wala talaga. So, thank you guys for coming today. Just please read those that I skipped today, specifically the proof of Darbo's theorem. Nandito naman siya sa lecture notes. Please download the latest version of the lecture notes. We'll start on Thursday on examples 11 and 12, go on with the properties of integral, and talk about the last result, which should be the highlight of Math 155, which is the fundamental theorem of calculus. All right. So until then, please start reviewing Para's preparations problem set. And don't forget to insert some rest along the way para hindi kayo ma-burn out, especially now na patapos na yung SEM, patong-patong na alam ko yung mga requirements na kailangan yung isubmit. Okay? So enjoy the rest of the day, guys, and let's see each other again on Thursday. Bye-bye.
Thank you.